To prove the Riemann hypothesis, a mathematician must demonstrate global arithmetic cancellation of the Möbius function. But many proposed operator models fail an immediate test. Their topologies inherently destroy the exact cancellation they are designed to study. Take the logarithmic translation model. The standard identity places Dirichlet monomials, n to the power of -s, onto a one-parameter character orbit. Applying the Bohr transform identifies prime logarithms with independent coordinates on a continuous structure known as a prime torus. This brings into play Kronecker's approximation mechanism, which identifies the vertical supremum of a Dirichlet polynomial directly with its Bohr lift on that finite prime torus. This is where Sarah Shuaib's paper identifies a structural obstruction. Because the unrestricted operator norm takes a supremum over the entire vertical character orbit, it effectively searches for and finds the exact worst-case phase alignment on that torus. When applied to the Möbius function, this optimization acts as an absolute value function. The alternating signs responsible for arithmetic cancellation are forced to perfectly align, replacing mu of n with its square, mu squared n. As a result, the full norm of a weighted finite Möbius translation sum equals its absolute square-free mass. The signed cancellation is completely erased. Because the unrestricted operator norm measures absolute mass rather than signed arithmetic oscillation, any attempt to reach the critical boundedness threshold using global operator limits is mathematically blocked from the start. We can observe the exact quantitative consequences of this phase alignment by testing the unweighted Riesz critical coefficient, where theta equals 1/2. This graph tracks the exact Möbius translation norm growth. The unrestricted operator norm tracks precisely with the square-free asymptotic limit. The divergence is exact. This alignment is an exact supremum limit, guaranteed by the norm's ability to search the entire orbit. Faced with this divergence, a standard mathematical reflex is to assume that regular, non-negative smoothing techniques, such as Cesaro or Abel smoothing, might repair the diverging norm. Corollary 3.4 of the paper strictly rules this out. Because the underlying limit evaluates absolute mass, no non-negative smoothing method can produce a bounded full-space limit at or below the effective Dirichlet exponent of q less than or equal to 1. The unrestricted operator norm acts entirely as a phase-aligned envelope. It measures the worst-case scenario, making it a categorically invalid proxy for Merton's cancellation and ensuring this instability is inescapable within the full space. If the critical line forces divergence, we have to map the exact boundary where bounded inversion actually functions. This plot maps the envelope operator threshold, defined by the weak offset. The solid blue line indicates the safe region where the unrestricted inverse converges. At and below the boundary, marked by the orange-dashed line, the full inverse diverges entirely, driven by the unsigned state exponent. This graph displays the condition number of the bounded inverse pair approaching the critical 1/4 barrier. The number blows up algebraically as it hits the absolute convergence boundary. This 1/4 value is exactly where the effective Dirichlet exponent reaches q equals 1. Bounded inversion is strictly a safe region phenomenon. Pushing the unrestricted operator algebra to the critical threshold guarantees mathematical breakdown before reaching 0. Since the global operator algebra is mathematically restricted to weights above 1/4, can the Riemann hypothesis be studied through operator models at all? This chart contrasts the full operator with the stable Riesz state. The blue bar shows the operator failing at the 1/4 barrier, while the orange bar proves Riesz state control continues through it. The green line shows the Riemann hypothesis requires state control where no inverse exists. The collapse of the full operator norm measures the worst possible phase on the prime torus, but this doesn't preclude a single stable arithmetic state. Any viable strategy must abandon the global norm, focusing entirely on controlling this specifically weighted state. Evaluating an isolated Archimedean state lets us bypass the optimization trap destroying the global norm. This graph details the behavior of the full operator norm, which strictly records the absolute square-free mass across different effective exponents. This plot shows absolute mass contrasted against the behavior of a gamma-weighted state, which acts as a localized frequency average. The gamma profile shown here forces down the remote frequency regions, suppressing the specific vertical characters, where the worst-case phase alignments, the blue spikes, occur. Applying this specific state energy yields an exact identity. It binds the Möbius translation product to the state vector, shifting the entire bounded inverse problem into a weighted L-squared space. This maps theorem 8.6. The Riesz criterion requires this state function in L-squared for alpha between 0 and 3/4. This forces an analytic Laplace transform, excluding response poles right of the alpha axis. Pushing alpha to 0 localizes zeros strictly to the critical axis. The Riemann hypothesis translates exactly to the state-specific stability of this one arithmetic trajectory, successfully evading the trap of the unrestricted operator. This matrix visualizes the exact finite gamma Möbius energy kernel that arises from this L-squared formulation. Because this energy state is derived from a norm, it is unconditionally non-negative by construction, generating the highly structured square-free sign pattern you see here. We must be strictly precise about what this accomplishes. The paper does not construct a self-adjoint zero operator, nor does it claim a while-positive factorization. This flowchart isolates the final barrier. On the left is the canonical explicit formula. In the center is the gamma-weighted state form. The mathematical reality lies in their unproven independent residual. Resolving this yields 4 strict outcomes: exact equality, positive residual, controlled approximation, or obstruction. The phase alignment trap has been rigorously diagnosed and bypassed using a gamma-weighted Hilbert space state. However, proving the Riemann hypothesis now hinges on resolving this independent residual, a precise, quantifiable problem that remains completely open.